The topic I will present is on the facility location problem in online and dynamic models. I'm Jia Xian. It's my honor to present the job on behalf of my collaborators. Now let's get warm up with the introduction of the UFL problem. UFL is short for Uncapacitated Facility Location. The offline setting is as follows. We are given a set F of facilities, a set C of clients, and a matrix over F and C. Each client is required to connect to an open facility. Opening a facility incurs facility costs, denoted as Fi. The connection also incurs connection costs. Here the connection cost equals to the distance between the client and the facility. The goal is to open a subset S in F to minimize the overall facility costs and connection costs. Here is a list of known results of the problem. The best current approximation ratio is 1.488 by Li. On the negative side, we have a 1.463 hardness. The most relevant algorithm to our work is the local search algorithm by Jaka Gupar, then simplified by Gupta, Tawanson, and Williamson-Schmaltz. The algorithm can reach a 1 plus square root of 2, roughly 2.414 approximation. Now let's recapture local search algorithm. Local search algorithm is to apply any of the following so-called local operation if it reduces the current cost, until no such operation can further reduce the cost. This so-called local operation includes open a facility, close an open facility, or swap two facilities. Swap two facilities, which means open a new one and close a currently open one. When we manipulate the facilities, we also rearrange the connection of the clients accordingly. These techniques provide a 3 approximation solution and can be improved to a 1 plus square root of 2 by scaling. Now let's move on to the online setting of UFL. In the online setting, the set of facility F is given beforehand, while the set of client C is not known at the beginning. Client comes one by one. To be exact, a client comes at each time step t. On the arrival of a client, we either connect it to an open facility or open a new facility to connect it. The decision is irrevocable. For example, at time step 2, here comes a client and we connect it to an open facility. Then, in the future, even a closer facility is open, which is apparently a better choice for this client to connect to. We are not allowed to disconnect the original connection and reassign this client to the closer facility. That's what we call irrevocable. Plus, a facility, once open, cannot be closed in the future. The competitive ratio in the online setting is defined to be the maximum of competitive ratio all the time. Here are some known results for this problem. Mason proved a big O log n competitive ratio, and it was improved by Fodages to be a big O log n over log n. Fodages also proved that the omega log n over log n is a lower bound. Now we begin to think, what if we are allowed to make a few changes to prior decisions? This probably brings a better competitive ratio. The assumption itself also makes sense. Revoking a decision is not prohibitive in most of the case. though the price might be high. So we consider online facility location with recourse. That's not much different from the setting without recourse. The facility set F is given beforehand and client come one by one. For each client, we need to connect it to an open facility or open a new facility to connect it. The difference is the decisions are revocable. We can make changes to the connections, and we can also close an open facility. We define the recourse to be the number of times we may change. This includes facility recourse due to closing operation and client recourse due to reconnection operations. The facility recourse is always no more than the client recourse. That's because when we closing our facility, we need to reassign those clients which were previously connected to it to other facilities. We also define the amortized recourse to be the recourse per client. The goal is to maintain a constant solution all the time while keep the amortized client recourse small. Our result shows that we can have a 1 plus square root of 2 plus small epsilon competitive algorithm with big O log n over epsilon amortized client recourse. Here we only show a competitive ratio of 3 algorithm instead, which can be easily extended to the better approximation ratio. In the following, I will first describe the algorithm and then do an analysis of recourse. The idea of the local search online algorithm is quite natural. When a client JT comes, we use a simple scheme called initial connect to do the connection. We either connect it to the nearest open facility or open a new facility to connect it, depending on which costs less. Then we try to do local operation to reduce the current cost, until no such operation is available. Based on the local search technique, this online algorithm has the potential to maintain a constant competitive ratio. The problem is, it has nothing to do to guarantee the recourse is small. Intuitively, we want to skip those local operations which only bring a tiny reduction in the cost. Those are the operations which don't contribute effectively in reducing the cost. So we can put a bar on doing local operation. We perform the operation only if it can reduce the cost by more than a certain amount. This comes to the definition of phi efficient operation. A local operation is called phi efficient if it decreases the cost by more than phi times the number of clients it reconnects. Roughly speaking, each reconnection is required to reduce the cost by at least phi on average. Now, the client might not be connected to the nearest open facility anymore. This because the reconnection to the nearest open facility might not pass the phi efficient criteria. From now on, we'll use S sigma to denote a solution. Sigma refers to the connection configuration, while S is the set of open facility to manage those configurations. Based on this, we can prove that when there are no phi efficient operations, we have the current cost is less than 3 times OPT plus a turn. The OPT here refers to the optimal current solution cost. Then we deliberately to set phi equals to this term. Then the right-hand side of this inequality turns to be 3 plus epsilon multiply OPT. That means When we apply the find efficient local operations until no such operation is available, then the current solution is a 3 plus epsilon approximation. Here we reach our first goal to maintain a constant competitive ratio. Next, we will analyze the recourse. First, we define delta t to be the difference of cost after and before initial connect of the client, Jt. Now we can prove the key lemma. For each time step t prime, we have the sum of delta t can be bounded by the optimal solution on t prime with a logarithmic factor. To prove the key lemma, we need to compare the delta t incurred by the arrival of client with its respective cost in the optimal solution at time prime. Let's say this is an illustration of the connection in optimal solution at time step time prime. We call an open facility with all of these connected clients a star. For example, this is called star I. This is another star. These two are stars too. Now let's focus on one star. In star I, J1 comes first at time step 1, J3 comes second at time step 3, J7 comes at third at time step 7, and so on. Here we have delta 1 for J1, delta 3 for J3, delta 7 for J7, delta 9 for J9. For each delta t, we can prove an inequality. The inequalities are brought by the find efficient property and some triangle inequalities. Note that the right-hand side of the inequalities are all costs in the optimal solution at time step t prime. And the denominator relates to the arriving orders. Then when we sum these inequalities, we get an inequality for the star I. The sum of delta t for star I is bounded by big O log t times the facility cost and the connection cost of star I. Then when we consider all the stars and sum up these inequalities for all the stars, we prove the key lemma. Now we can prove the recourse is small. The key lemma tells us the prefix sum is small. The find efficient local operation requires that each reconnection reduce the cost by at least 5. So the total recourse per client can be bounded by this term divided by 5, and it yields big O log t over epsilon with a factor log d, where d is the aspect ratio. The log d factor can be removed by dividing the algorithm into stages and frees the clients arrive 2 stages before the current stage. We define a stage as follows. Let's say begin with some time step. Initial is the initial cost. A stage ends if the current cost is larger than the initial cost divided by epsilon pi. Then, when we are in the P stage, we freeze the clients arrive before P minus 2 stages, which means those clients will not be considered in the current stage. For the facility that has been opened in the previous P minus 2 stage, if they are still open in the current stage, we need to recalculate the facility cost. In this case, we lose a competitive ratio. The ratio is epsilon prime, the sum of epsilon prime from degree 1 to p minus 2. Though using such a small factor, we can remove the factor of log d in the previous results. So finally, we reach our result big O log t prime over epsilon prime times log 1 over epsilon prime. This concludes our main results. We then turn to the dynamic algorithm model for the problem, where we care about the update time instead of recourse. The goal is to design fast algorithms that may take good solutions at all time steps. We reach the conclusion that we can maintain an approximation factor of 1 plus square root of 2 plus epsilon with total update time of big O n squared poly log n. Note that reading the metric has already taken n squared time. In this algorithm, whenever a client comes, we use a similar simple rule to accommodate it, like the initial connection. But now we cannot afford to consider all possible local operations. Instead, we use the randomized local search idea. We design a procedure to do randomized local search. We call the procedure only if the cost of our solution has increased by a factor. Then in the analysis, we prove a similar lemma to the key lemma, which also shows that the total increase of the cost due to the arrival of client is small when compared to the optimal cost for these clients. Then we use this to bound the number of times we call the procedure. This briefly describes the picture in the dynamic algorithm. Finally, we started the fully dynamic model for facility location. In this setting, clients can both arrive and depart. Our main result is, for HST matrix, we can prove there is an algorithm that achieves O1 approximation factor and big O n poly log d total update time. Then with the seminal results, which shows that any arbitrary endpoint metric space can be embedded into a distribution over HST space such that the expected distortion is at most big O log n. The first result implies that for any arbitrary matrix, there is an algorithm that achieves big O log n approximation factor with the same order of the total update time. This concludes my presentation. Thank you for your time.